This is a review of the test that, on covalent bonding, and I just want to run through some of the answers and talk about it a little bit with you. So this question here, yours might be scrambled in a different way, but if you follow the question, you can find it on your test. Which of the following molecules is a polyatomic ion? Well, first of all, take a look at the word here, ion. Ion implies that the molecule here has a charge on it, whether positive or negative. Notice the rest of these molecules have a neutral charge because they have the same numbers of electrons and protons within them. An ion, however, has an imbalance between protons and electrons. This has 2 extra electrons in it. Now the polyatomic part means that the formula has more than one element within it. This has 1 sulfur and 3 oxygen. So this is clearly a polyatomic ion. Now in this case, we want to find out how many valence electrons are needed to complete the picture. How many pairs of valence electrons. So if we take a look at this picture, we'd see, let's go ahead and do an inventory of the number of valence electrons we need. We have 1 phosphorus, we have 4 oxygens, and I notice we have 3 hydrogens. So let's figure out from that number of elements what we're going to need. So just adding them all up here. Phosphorus has 5 valence electrons. Each oxygen has 6. And each hydrogen has 1. So let's see, that would be 6 times 4. This is 24 plus 5. So that's 29 plus 3 for the hydrogens is 32 total. All right, so now to figure out what we've already got on here, each of these lines is equal to 1 pair. So we have 2, 4, 6, 8, 10, 12, 14. So we've already got 14 in the picture. So if we subtract these off, let's see here, I'll carry that. I need 18 more electrons in there, which is equal to 9 pairs of electrons. Now to show you where they would go, this phosphorus is already complete with its 8 valence electrons. This oxygen here needs 2 pairs. This oxygen here needs 2 pairs. This oxygen needs 2 pairs. And this oxygen actually needs 3 pairs. Notice now they all have their full octet. So the answer to this clearly would have to be D. 9 pairs are needed. So water has how many unshared pairs of electrons? So let's go ahead and write out the formula for H2O. That's water. Let's see, now water is a neutral molecule, meaning that oxygen with its 6 valence electrons and hydrogens got 1 each. So in this picture I need to show a total of 8 valence electrons. Alright, so here I have 2, 4, so I need to put a couple of unshared pairs on this oxygen like that. So I see here 1 pair, 2 pairs of electrons are unshared. These are now the shared electrons here. These are the unshared electrons, so we actually have 2 pairs of unshared. Total number of valence electrons in this molecule. Okay, so sulfur, and I have 4 oxygens. And then I have this -2, which means I have 2 more electrons. So sulfur has 6, and oxygen has 6, and oxygen has 6, and oxygen has 6, and 6, plus these extra 2. So 6 times 5 is 30, plus 2 is 32. It's just that easy. So the total number of valence electrons is 32. So what is the cation in the formula KMnO4? Well, KMnO4, if you split it right down the middle here, is not exactly in the middle, but this is where the positive K is +1, and the MnO4, if you look it up, is -1. You can look this up in the book on, I think it's page R52, or maybe it's on page R54 in the back of the book. Of course, potassium is a +1 ion. The confusion is that the Mn is a part of the negative ion here, negative polyatomic ion. So the cation is actually just K, which is not covalent bonding. So covalent bonding tends to happen between two nonmetals. So if you look at the total periodic table, this part of the table over here is the nonmetals. I'll make Mn, and then the metals are generally the rest of the table. So covalent bonding is generally two elements from within the same part of the right part of the table. Well, ionic bonding is when you have an element from over here combining with an element from over here like this. You see, these elements tend to become positive charged, and these tend to become negative charged. So we're looking for a metal and a nonmetal. So these are two nonmetals. This is a nonmetal bonding with itself. Two nonmetals, two nonmetals. The answer is KCl is a type of ionic bonding. Okay, so it's not covalent at all. The answer would be B. Which of the following is a monatomic ion? So ion means it has a specific charge. So this one has a charge of -1, but it's polyatomic. So that's not a monatomic. Monatomic means just one element. So here's an ion over here with -1, but again, that's polyatomic. This is not an ion at all, and nor is this water. So this is the ion that's monatomic. It's the chloride ion. The answer in this case would be A. So now we have a number of dot structures. One of these is wrong. So the way you would figure out if it's wrong is, first of all, count the number of valence electrons and see if the number is right here. So this one should have 6 and 4, 1 and 1 for a total of 12 valence electrons. Counting them up, 2, 4, 6, 8, 10, 12. So it does have the right number. And each of these has the right number of valence electrons. Hydrogen 2, carbon 2, 4, 6, 8. And this oxygen is 2, 4, 6, 8. So this is actually perfectly good. This one has carbon, which has 4. Oxygen has 6. For a total of 10. 2, 4, 6, 8, 10. So this one's okay. This one here, oxygen has 6. Sulfur 6, and oxygen has 6 for a total of 18. So let's count it up. 2, 4, 6, 8, 10, 12, 14, 16, 18. It's got the right number. So this one here has to also be correct. Here, phosphorus, 4 oxygens and 3 hydrogens. So the phosphorus has 5. The 4 oxygens is 6 times 4, or 24. And then the 3 hydrogens, for a total of 9, 10, 12, would be 32 total. Let's check it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That one's also okay. Here, let's see. So oxygen has 6, bromine has 7, hydrogen has 1. We should see a total here of 14. So here we go. 2, 4, 6, 8, 10. So this is wrong. Obviously, this oxygen needs a couple of pairs right here. So here is our one that's wrong. Answer is E. So which of these is correct? For nitrogen. So nitrogen, as you know, has 5 valence electrons. And this is not an ion of any kind. So we should see 10 valence electrons in this molecule. So 2, 4, 6, 8, 10. Well, that one right there looks good. 2, 4, 6, 8. Nope. 2, 4, 6. Nope. This has just got 6 also. And then 2. The correct answer is obviously A. So which one of these is correct for nitric acid? And this looks very complicated, but start and keep on doing the same thing. So nitrogen, as we know, has 5. Each oxygen here has 6. And then the hydrogen has 1. And there's no ion at all here. It's a 0 charge. So adding this up, we have 18, 19, 24. That's the amount that we need in each of these molecules. So let's just check the first one. Do we have 24 here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. This one right here looks good. Now let's check this one. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. This one also has 24. But do we have a problem here? Yes, we do. Notice that this nitrogen has too many. 2, 4, 6, 8, 10. So it doesn't want to go to 10. It just wants to go to 8. Now this one I don't think has 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this doesn't have enough valence electrons. This one has a double bonded hydrogen. That never happens. And here I can see the nitrogen only has 3 bonds. So the correct answer should have been A. Which of the following is the polyatomic ion? We've already seen one of these in this test. Polyatomic is one that's, first of all, an ion. See, these are all 0 charges. And so none of these could be ions. And of course, this is a polyatomic also. Answer is C. Which of the following is a dot structure correct for NO2, 1 minus? Let's analyze NO2, 1 minus. 5 valence electrons. We have 2 oxygens plus 1 bonus one here. So it's 12 plus 6, or 18. So we have to find the one with 18. And 18, all of them should have octets. Now this one's wrong because it's an ion, but there's no brackets. See these brackets? So this has brackets, all right. But let's check the number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Let's try that again. 2, 4, 6, 8, 10, 12, 14, 16, 18. So this has the right number of valence electrons, but let's just check these. This has 2, 4, 6, 8, 2, 4, 6, 8, 10. See, that's not going to happen. Now this one has 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, it does have 18, but this oxygen has 2, 4, 6, 8, 10. So that can't be right. This one has 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes. This has 8 and 8 and 8. This looks to be the right answer. But just to double check, and this one certainly doesn't have enough valence electrons, so the answer turned out to be D. Which of the following explains the mistake in this problem? Let's see. Well, first of all, hydrogen shouldn't have all those valence electrons. However, let's go ahead and take a look at the number that should have. 6 and 4, 1 and 1, so 10. I should only have 12 valence electrons, whereas I have 1, 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have far beyond the 12. There should be fewer valence electrons in the picture. How many valence electrons are in this picture? Well, we have 4 and 4, 4 and 4, and then each of these has 1. Okay, so we have 4 times 4 is 16 for the hydrogens. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So I see 26 here. Looks like the answer is probably B. So the molecule shown above has a formula of. So now remember, this is one of those special kinds of pictures where they have, it's kind of complex, so they don't show all the atoms. And whenever you see a funny little jig or a jog like this, you put a carbon in there. And notice you only put carbon in if you're wondering what's going on. I never put an oxygen or hydrogen or anything else. Only add carbons to these little jig places here, where there's a little angle that looks funny. Now once you've put the carbons in properly, then you have to check to make sure they all have 8 valence electrons. So 2, 4, 6, 8. This part is perfect. This carbon, on the other hand, it's 2, 4. So I'm going to have to put hydrogens on here. You do not put unshared pairs on the carbon. This is just the way it works. You have to add a couple of hydrogens to make this complete. In fact, the same thing would have to happen here. So these are the hidden hydrogens they didn't tell you about. Let's see now, what about the rest of the valence electrons? Well, now this oxygen needs 2 pairs. This one needs 2 pairs. And this one needs 2 pairs. This one needs 2 pairs. And this one needs 2 pairs. So does this one. And so does this one. So this is actually the total dot structure for this molecule. But we're really finding the formula, so let's go ahead and count up the atoms of carbon. 1, 2, 3, 4, 5, 6. So going through here, looks to me the only possible answer is B with 6 carbons. Double checking. 1, 2, 3, 4, 5, 6, 7 oxygens. Yes. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Clearly the answer is B. So this is a polyatomic ion. What would the charge be on this? So the formula for this would have to be PO4 with some unknown charge up here. Now, by the way, if you look this up on page R54, you would notice that this is actually called phosphate. So right there, it gives you the clue as to what the answer is. You could look that up, but let me tell you how you'd find it otherwise. So first of all, we have these valence electrons. And let's see how many of these atoms themselves would contribute. Oxygen would have contributed 6 and 6 and 6 and then 6, and this would contribute 5. So when we add these up, we get 6 times 4 is 24, plus those 5 in the middle is 30. So we should have from these atoms alone 30, but let's go ahead and count the actual valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need to double check this again. Now, did I get that right? Let's see. So 6 times 4, 24, and 5 is 29. Excuse me, I did that wrong. So this is 29, okay. And then I noticed when I add them up, I got 32. So the answer is, I see 29 from the atoms, but when you count up the dots, we have 32. So if you look at the difference of 3, this must have 3 bonus electrons in it, which actually, if you look it up, is what phosphate is. So this is going to be 3 minus. What is needed to finish this picture of NCl3? Well, first of all, let's check the number of electrons. 5, 7, 7, and 7. So 7 times 3 is 21, and 5 is 26. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. Okay, so we'll check that again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. So I have enough valence electrons. But the nitrogen here only has 6 valence electrons. I'm going to need to, let's see now. I'm going to need to bring in a couple of valence electrons, I would think. Let's see. Oh, I know what it is. The nitrogen here has 2 valence electrons, and I'm not showing them. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so there I have my 26. So actually we needed to add 1 pair of unshared electrons onto the nitrogen. Which of these dot structures is incorrect for neutral atoms? If you look on the periodic table, it tells you how many valence electrons the neutral atoms have. Group 1, group 2, then we have the transition metals, so don't worry about them. And then, of course, we have these other groups, 3, 4, 5, 6, 7, and 8. the noble gases here. So beryllium is right here, and that's group 2, so it's good with 2. Chlorine is right about here in group 7, so it's showing 2, 4, 6, 7. It's good. Argon is right about here on the table. It has 8. Yeah, it's showing 8. Silicon is showing 4. Let's see, silicone is 3, 4. Silicone is right here in group 4. So that's group 4, 5, 6, 7, and 8. So it has 4, fine. And hydrogen is over here in group 1. And so it should show 1 valence electron, but it's not showing 1 valence electron. So see, this doesn't have the charge of a neutral atom. In fact, this would have to have a -1 charge, the hydride ion, because hydrogen only has 1 valence electron. Here it has a bonus electron. Certainly not neutral. So what's wrong with this picture? Well, this is a capital L. Sorry, but it should have been chlorine with the lowercase l. So make sure you get the symbols right. Which has the same numbers of valence electrons. So you're actually looking at the vertical column that they're in, and which of these elements is in the same vertical column. And you look carefully, you see that these 3 are noble gases at the end of the table, and they're in the same vertical column. Now what we're looking at here is a metal and a nonmetal giving electrons to the nonmetal. So after this gives over its electrons, it becomes +2, and each of these become -1 ions. So let's see now. We're going to end up with the formula where you have 1 magnesium and 2 iodines. Oh, obviously this is it right here. Always put the metal on the left, like they're showing, not like this. For this molecule, the correct dot structure. So first of all, let's count them up what we need. 4 and 5, and then 1, 1, and 1, 9, 10, 11, 12. So the correct dot structure should have 12. 2, 4, 6, 8, wrong. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. That's the correct number. Do they all have 8? Well, let's check this. Carbon has 2, 4, 6, 8, 10. So see, carbon has 10. 2, 4, 6, 8, 10, 12. Well, that's the correct number there. But let's just see. Carbon has 2, 4, 6, 8. 2, 4, 6, 8. So I'm going to check that just for a second. That could be the best answer right there. This one has 2, 4, 6, 8, 10. That doesn't have enough. 2, 4, 6, 8, 10 doesn't have enough. The best answer would have had to have been C. How many unshared pairs are lacking? So I can see right now that fluorine, it needs to have 3 pairs of electrons for a total. Remember, it has 7, 4. Each of these has 1, so 7 and 4 is 11, 12, 13, 14. 2, 4, 6, 8, 10, 12, 14. So with those 3 pairs, how many unshared pairs? 3 are lacking. So the dot structure for this ion, okay, so carbon is in the middle like it says, and on the outside we've got the oxygens. Now, carbon has 4 valence electrons, so I'm going to go ahead and just kind of throw them into the bond. Each of these oxygens has 6, so I'm going to start out by just putting them on the outside here just to keep things simple. And then I'll put these down here, 6. Now notice I have 2 valence electrons as bonus electrons. So because I have nothing here, I'm just going to put the bonus electrons in right there. I'll make them X's so you can see. But they're no different from the rest of the electrons. So here I have the basic idea, and it looks good. I have 8 valence electrons and 8 and 8, but this carbon only has 2, 4, 6. So what I'm going to need to do is bring in another 2 electrons. Well, in order to do that, I'm going to have to rotate 2 electrons around and put them into the bond on one of these oxygens, just one. So if I rearrange this a little bit, let me just make it less messy. The answer would come out to be like this. Put in 2 dots there, and 2 there, and 2 there. Of course, once you put in the dots, that's fine. 4, 2, and 2. Now, just to show you what it would look like with lines, if I erase these, okay, that's nice. And then I would put in 2 lines, 1, and 1. Almost finished, but remember, this is a polyatomic ion, so before I leave it, I need to put in the brackets and the -2. Okay, there it is. SO2. So S has 6 valence electrons, and both of these oxygens has 6. And then I have 2 extras for a total of 20. All right, keep in mind, the 20 has to be the right number at the end. So the sulfur is in the central, and oxygen's on either side. Okay, great. Let me try the same strategy. I'm going to go ahead and put in these electrons pretty much any which way I want. And then from there, we'll work on it. So I've got the 6 there, and the 6 there, and the 6 there. I also have 2 bonus ones, which for the moment I'll put in down here. So I have 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, which is the right number. Oxygen has 2, 4, 6, 8, sulfur 2, 4, 6, 8, 2, 4, 6, 8. This is actually a good answer right here. I'm going to go with this one as one of the possible answers that fulfills the criteria. And brackets -2, it's good. ClO. So chlorine has 7, oxygen 6, and then 1. So that's 14 total. All right, let's go ahead and draw it in. Chlorine and oxygen. So chlorine has 7 valence electrons. Oxygen has 6 valence electrons. And then the 1 bonus electron, I'll put it right there so I have all paired up. 7 and 7, that's right. So this is the way it could be with 2 dots, brackets, and -1, and I'm done. And of course, if you don't like the brackets, you could erase that and go ahead and put your line in right there. Perfect. So finish the molecule above, hydrogen carbonate. So hydrogen carbonate, I'm giving you a hint as to what the formula looks like. At least this tells you how many bonus electrons should be thrown into this. And so let's add them up. We got 1 and 4, and 6 times 3 is actually 18, and 1 bonus electron. So 18, 19, 20. We should have 24 total in this molecule, so keep that in mind. Right now we have 2, 4, 6, 8. So I have to add a lot more to get to 24. So I'm going to go ahead and add some unshared pairs on this. Unshared pairs here, here. Carbon does not like unshared pairs, so be careful with that. It just doesn't like them. Now let's double check to see if I have 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. Double check that again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26. I have too many valence electrons in there. I only get to put 24 in, so I'm going to have to erase a couple. All right, well, there it is. Now I have the right number of valence electrons, 24. So now I'm seeing my way through this. This oxygen here only has 3 valence electrons. I mean 6, 2, 4, 6. This carbon only has 2, 4, 6, so we're really desperately in need of a double bond here. So I suppose if I swung these two around here, something just doesn't look right with this thing. I'm going to end up with a -1 here. Let me just go back and double check, make sure I'm thinking right. 1, 4, 18, and 1. So 18 and 2 is 20, 24, that's correct. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. No, actually I need another pair. So sorry about that. I need to bring in another pair, but I'm going to go ahead and bring that pair in here as a bond. That's what I was needing, because now I've got 24, and this one has 8. This one has 8, 8, 8, and see, that's what I needed. I had to make sure I counted them correctly. And so then if I put the -1 on there, this is the correct answer for hydrogen carbonate. Almost finished. So here we have this molecule. This is a little more difficult one. We'll work our way through it. So remember, this is one of those kinds where you have to put the carbons in. And this little stick out here was tricky. This is one that has a carbon at the end. Only add carbons to these places like this. And after that, if the carbon only doesn't have enough bonds, add hydrogens. So we saw one of those actually in class, a tricky one, but we did one of those in class, so you had a chance to look at it at least. So now I'm going in and adding carbons wherever there's one of those angles and an element is needed in this ring. This is okay, so here I actually got 6 carbons to add here to this piece. Okay, so far so good there. Now let's go back and check these carbons. So this one is going to need 3 hydrogens on it. Oh, here's another carbon that goes here. And this one has 2, 4, 6, 8. That's good. This one needs a hydrogen. This one needs a hydrogen. This one needs a hydrogen. So does this one. Now this is complete. This nitrogen only is showing 6 valence electrons. It needs an unshared pair. This one needs an unshared pair too. Don't add hydrogens to these nitrogens. Only add the hydrogens to the carbons, please, not to the nitrogens. Okay, so now this oxygen is still in need of 8 valence electrons. This one also can take those unshared pairs. This one needs 2 unshared pairs also. So does this oxygen. Okay, it's working our way around. Get over here, that one's good. This one needs a hydrogen. This one needs a hydrogen. This one needs a hydrogen. Needs a hydrogen. And needs a hydrogen. Excellent. Okay, that molecule is complete. Checking the formula. Carbons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I bring down here, I put in 16 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Apparently there are 14. Nitrogens, I see 4. And oxygens, I only see 2. Okay. Last problem, calculate the RF for this chromatogram. Now, as we learned in the lab, the RF is the ratio of the distance the dot traveled to the ratio of the total solvent travel. The solvent travel is the denominator of a fraction. The numerator of the fraction, the 2.1, so if you do the division here, you find out that 2.1 divided by 2.8 is 0.75. That means that this thing traveled about 3/4 of the way. I mean, if I show you this, maybe halfway there, so 1, 2, 3 to 1, this is 3/4 of the way, or I suppose you could view it as 75%. But this is the actual RF, not the 75%. Now be careful. You have to divide these numbers. You don't take 2.8 and subtract 2.1. That comes out close, 0.7, but as you can see, that's totally wrong. Okay, so that wraps up the test. Thank you very much.